Hello everyone, welcome back to VCodes. This video is part of a series of videos where you will be able to test your VHDL or VHDL coding skills. I will share code snippets which you will need to debug. The video will have two parts. The first part will have the code and its simulation and the desired output. After watching this part, you could pause the video and try to solve the issue by yourself. After a pause, I will share the solution with you as well. Please make use of these upcoming videos to get more practical knowledge of VHDL. Thank you. This is the VHDL code for a random access memory RAM. This RAM is written as a generic RAM, basically meaning that the width of the RAM and the depth of the RAM can be changed by just changing these values over here. So address width means 2 raised to 8 is equal to 256 locations are available in the RAM, which is the depth of the RAM, and the data width is set as 16. So each element is 16-bit wide. So that's what these numbers mean. So we have a clock and reset input here and an address input which is declared as unsigned. The size is set as address width -1 down to 0. Okay, and we have a data in, which is the data which will be written to the RAM if the write enable signal is 1. And then we have a data out, which is the value stored in the location specified by this address. And now over here in the behavioral part, we are declaring the memory. Okay, so first we start by declaring the type of the RAM memory, which is 0 to 2 to the power of address width -1. So basically it means that 2 raised to 8 is 256 -1, so 255. So you can read it as this array 0 to 255 of unsigned data width -1, which is 15 down to 0. Okay, so this specifies the number of elements in the RAM, the depth of the RAM, and this mentions the width of each element. Okay, and then I am using that type over here and declaring it as a signal RAM underscore mem, and all the locations are initialized to 0. Now we have a process with the sensitivity list as clock. On every rising edge of the clock, if reset is 1, it's a synchronous reset. If it is 1, I am reinitializing the RAM memory. Okay, I am erasing all the contents. If reset is equal to 0 and if write enable is equal to 1, then I am writing the contents of data into the RAM memory specified by this address. Okay, so to integer is a function available in numeric standard. It converts the address value, which is in unsigned format, into an integer. Okay, because the index has to be mentioned as an integer. So outside the process, data out is always assigned as the contents of the memory located by the address value. So this is our code, and we can just go ahead and synthesize and see how it is doing. Alright, it's finished. Let's see the synthesis report. So I want to bring your attention into this part. You can see that found 16-bit register for signal RAM mem1 and so on until it goes here. Okay, so what is this thing? So based on this text, there is also an info given by XST which reads as 4096 flip-flops were inferred for signal RAM underscore mem. So how this number came is like 256 is the number of elements in the RAM and each element is 16 byte. So 256 multiplied by 16, you will get 4096. So 4096 flip-flops were inferred for signal RAM underscore mem. You may be trying to describe a RAM in a way that is incompatible with block and distributed RAM resources available on Xilinx devices, or with a specific template that is not supported. So what it says is that each FPGA board has some or other inbuilt RAM and other resources. So when we write a code, it's the tool will try to use these inbuilt resources if it is possible, because using the inbuilt RAM for doing what we want is much faster. So in this case, the tool tried to use it, but it couldn't because there was something off with our code. So what is that? That is the question I would like you to try and answer. Okay. So this is the code, and tell me why this code is not able to use the inbuilt RAM inside the FPGA. Okay. You can pause the video and work out the solution. In few seconds I will explain you the mistake in the code. So I hope you were able to solve this problem. So if you couldn't, it's fine. Let me explain to you. So the problem was here. So you can see that I have given a synchronous reset. It looks like a very simple thing, but it's just a big no for synthesis, because what we are trying to do is on the rising edge of the clock, when the reset is equal to 1, I am trying to erase the content of all the RAM. That means, like, in one rising edge of the clock, I am trying to write all the locations, all the 256 locations inside the RAM, which is not how a RAM works. In a RAM, when you write a value, you do it in one clock cycle. Then you write another value to another address, you need to wait for the next clock cycles. That is how it works. But if you try to write zeros into all the locations in one go, that means you cannot use a regular RAM to implement this functionality. So we have to change it. What we have to do is we have to write zeros to the RAM one by one instead of doing it in one go. So let me modify this code and show you. So I have modified the code. So I have declared a counter which has an integer range of 0 to 2 raised to address with -1. So this counter can count from 0 to the last element address, and which is initialized to 0. And inside here I commented out this line which was causing the problem, and I added this part. So what I am doing here is I am incrementing counter from 0 to this value. When this value is reached, I reset counter to 0. Otherwise I just increment the counter, and for each value of counter I am just assigning 0 to that memory, and each value of counter is used as an address to the RAM memory, and I am writing zeros to them. Since our RAM has a depth of 256, this will take 256 clock cycles to do this whole operation, but we will synthesize this code and see how it makes a difference. So the synthesis has completed. You can see that it's showing a minimum period of 2.235 nanosecond and a maximum frequency of almost 450 megahertz. This information wasn't available for the first code. So let's see the synthesis report. So you can see that those usage of flip-flops is missing in this report. So going down, you can see that there is one more info. There is that means we could do some improvements. Could see that because you have described an asynchronous read, or because of currently unsupported block RAM features. So asynchronous read, which is this one. So we are reading the value of RAM memory all the time. Unfortunately, this particular FPGA doesn't have a RAM which is able to do this. So what we could do is we could just copy paste and put it under here. So only at the rising edge of the clock we will be reading the contents of the RAM. Okay, let's synthesize it again. So we have completed the synthesis, and you can see that the maximum possible frequency is increased from 450 to 492. So there is some improvement. Let's see the synthesis report now. So looking at the report, after advanced HDL synthesis, the info says the RAM will be implemented as a block RAM, absorbing the following registers. So you can see that this means we are using an inbuilt RAM for the RAM code we have written. That is why we got a much better frequency as an operating frequency. You can also see that it's a dual port RAM, port A and port B, and you can see that the address A goes as the address input for port A, and here the address B is connected to the counter signal, which is what we are using for reinitializing the RAM to 0, and the data input to the port B is connected to ground, which means 0, because we are using port B only to initialize the RAM to 0. So you can see that by modifying the code we have aligned much more with FPGA we are using. So I hope you learned something new from this, and the main conclusion from this video I want to tell you is that when you are writing a code in VHDL, always think in terms of hardware. Like the experts say, don't think software but think hardware. So whenever you are writing a code, you should think what kind of hardware will be the result when you write this code, and if such a hardware is feasible, because this is not C programming, and if a necessary hardware structure doesn't support it, the tool will either take a long time to synthesize it or it will even fail. So always think hardware when you are writing code in VHDL. Alright, I hope you enjoyed this video. Please like this video and subscribe to my channel for more such videos in the future. Bye bye.